Okay, so this presentation is going to talk about some anti-forensic topics, and the first thing we're going to do is talk about a program I recently wrote called Obfuscator, and it's not completely finished, but the part I want to show you is finished. So first we have to talk about bit shifting and rotating. So there's a YouTube video that actually does a pretty good job of talking about bit shifting, and I'm going to show you that, and then we'll talk about rotating using my favorite editor, Notepad, here. Okay, so this short animation will give you the idea of shifting right. So here we have a value 10011011. That's the initial binary value, and this is going to be where the bits get placed, and then this animation will show you the results of shifting right. Notice that as it shifts right, it's always losing the rightmost bit. If you shifted left, you'd be losing the leftmost bit. And at a certain point, you've lost all the original bits, and you're just left with 0. And there is a solution for this. There are actually two solutions in the obfuscate program that we're going to be taking a look at. So obviously, if you obfuscate any kind of data, you can't lose data. You've got to be able to do a complete reversal on the data that you've obfuscated. So here again, if you have this data, and as you shift right, you're replacing any shifted bits with a 0, and you lose the rightmost bit. So that's really bad. Go back to the other value. Now there is one solution. You might have a whole bunch of data. Okay, that byte. So these are different bytes. Let me put a dash in there. Oops. Okay, so let's just talk about this. So let's say we shifted this over. Again, that's replaced with a 0. What we could do, that's a 1 there. So now as we shift this over, put the 1 there. And as we shift this over, put that 0 there. And this 0 will come back to the beginning and get placed right there, which it was a 0 anyway. So what we can do is we can holistically shift the entire document, not just one byte or one word or one D word. Okay, so that's actually the part I haven't done in the obfuscate program, that I haven't done the holistic shifting, and that's going to be one of your optional assignments. But what I have done is implement a rotate. So as you shift over, you take this value each time and rotate it back. Okay, so that's one rotate. We rotate again. Take this value off and put it at the beginning. See how we're just doing a rotate, rotate, take this value off, put it at the beginning. So every bit that falls off the right side gets plucked off and inserted in the beginning. That's a rotate right. If I rotated left, like for instance here, that left bit would just be tacked on there, appended there. So that's how shifting and rotating work for binary values. And the way my obfuscate program works is you can either shift or rotate. When you rotate, it's rotating individual bytes, words, and D words. When you shift, it's shifting holistically all bytes or all words or all D words in the document. And in both cases, you don't lose any data. As I said, I haven't implemented the bit shifting yet, and that's going to be one of your optional assignments for this section. So I know that this semester is focusing on Linux, but it's okay. The logic is the same in Windows. I'm going to start off, I developed this application in Windows, and so we're going to start in Windows, and then I'm going to move over to Linux and compile it and show it to you there. It's really the same code. It's all ANSI C. So it compiles in both environments. So the first thing, and we talked about this last video, is I've got my defines. This is do everything by byte, do everything by word, do everything by D word. And this is actually what we're doing. Do roll, rotate, do shift, go right, go left. So you can actually go either direction, right or left. And here are my prototypes. So this is similar to what we talked about on the last video. So let's take a look at the main program. And the idea is you always want to try to keep your main program fairly simple. As you can see, this is fairly simple. I got some global variables, which for a program such as this, it's not object-oriented, and these global variables just make it a lot easier to do stuff like this. And I know people want to frown on global variables, but in this case, they actually are pretty handy. So the data size, that's what I'm going to perform the operation on. Defaults to bytes. The change type, we're going to do rotates by default. The other one is shift. We're going to by default go right. And the distance, see, we can roll or shift as many as we want. So I might want to roll or shift 1, or I might want to roll or shift 5. And see, this gives you more options as far as obfuscation, because let's say someone knows that you're always rolling or shifting 1, then it's really easy for them to reverse engineer it. But if they don't know the value, then it just makes it a lot harder for them. These are the file names, the file paths, the in file, the out file. Okay. This is going to contain the file data once it's loaded and the file length once it's loaded. So here again, let's just take a look at the main. We're going to parse the arguments, command line arguments. This whole program is based on command line arguments. We call the helper function to load the actual file data. And we call this do it function. The do it function actually does the rolls or shifts or whatever it's going to be. And we actually save the file to disk. So that's the getting started part of this. So the do obfuscate module is the one that actually does the work. I know the support stuff is really important because sort of shuffling that outside of the actual obfuscation logic is good for the understanding of the program. But here's this do it method, this do it function. Depending on the direction, you either obfuscate left or right. That's shift or rotate left, shift or rotate right, depending on what it is. So by default it goes right, and we'll just take a look at that. That's left. Here we go, obfuscate right. And notice that I've got 3 pointer types because we can either do this by bytes or words or D words. Bytes, words, D words. Okay, so we've got all 3 pointer types. That's actually a pretty efficient way to do it. And then we switch on the data size, whatever we're going to use to work this. Here's by byte, here's by word, and here's by D word. And you notice if I have the code for if it's a rotate, but I have no code for if it's a shift. I've implemented the rotates. I haven't implemented the shifts. If none of my brilliant students do this, I'll do it next week. But for right now, I didn't have the time to get it done before today. Okay, so by default we do a byte and we do a rotate. So it's going to come here. It's going to do every single byte. And here again, don't forget you're not losing any data because it just rolls the data, rotates the data. So rotate byte right. Let's go. And this just does it 1 byte at a time. Okay. So it gets the data. And the distance is how many times we're actually going to rotate this. It could be really any number. And the reason we are doing this, once again, is so that the obfuscate program has extra parameters that you, the obfuscator, would need to know, and that the examiner would have to guess or continue to sort of do trial and error. So we get the rightmost significant bit here. Okay. Remember, we've got to preserve. We've got to preserve data. We've got to preserve the data, and we bit shift it left. So now it becomes, instead of the least significant bit, it becomes the most significant bit. We shift our data right, which means we're going to drop one of those bits off. But whatever it was we found directly to the right, we're going to now or it back in. So basically this is a rotate that does not lose any data. Finally, we put this value back into the buffer in the same exact place. So that's really all it does, and that's all there is to the logic. And what I'd like to do is invite people in this class to go ahead and do the actual shift. Remember, you have to do the holistic shift of the entire document. So that's shift byte, word, D word to the left, byte, word, D word to the right. Okay, so here I've got my flash drive containing that code. I'm going to go ahead and copy that on into my home directory. Okay, it's there. Get rid of this stuff. Open up a terminal. So I should see all those files here. Okay, and those are the same files as I was using in Visual Studio and Windows. So let's quick take a look. Same exact code, right? And so forth. It is the same code. Okay. Okay, so let's go ahead and compile this. I've got 3 C files and 1 H file, and we don't have to specify the H file here. And we'll say obf obfuscate for the output file name. Okay, and if I run the executable, it's going to give me a usage because I don't have any. Oops. Okay, so it's going to give me the usage. It looks like I need a \n there, but let's go and fix that now. So this should have a \n here. Okay. Now it should give me a decent. Okay, very good. So that's all there is. I'm going to invite you to finish this program by adding the shift code and to experiment in Linux to understand it fully. Okay, so in pursuit of anti-forensics, data hiding, those types of topics, we're going to talk about steganography a bit right now. Now, the most common steganography type is image steganography, although it can include just about any kind of file, file type or media type or data type or whatever. But I found the easiest to explain the topic, the concept, is through the through image files. And BMP and PNG are they're lossless file formats. JPEG is a lossy file format, which actually you lose data with JPEG when you actually compress it. So I'm going to skip over JPEG. That's a much more lengthy topic. So I'm going to skip that right now. This topic will easily relate to BMP and PNG. Okay, so here I have 2 blue squares, and blue obviously has all the blue channel as 1 and all the other channels as 0. And notice I haven't stripped any bits off, but I'm going to strip a single bit off, and you can see the stripped blue color just has that 1-bit strip, but you can't see any difference in these two panels. Let me strip the 2nd bit off. That's because the most significant bits are still set and only the least significant bits are set. And I actually have some slides where I'm going to talk about this a bit more. Let's go ahead and see where it is. You can almost detect a bit of a slightly darker shade there. It's 4 bits, so you basically stripped off. Finally, when you get down to 7 bits to strip, it's a lot darker. Okay, let me select another color. Let's do it like a green. And let's go ahead and strip off none. And we'll see. So the point of this is that you can actually strip bits off without necessarily affecting. Yeah, that you can actually tell that quite a bit. Do one more color, say we'll do like a reddish color. That is a red. Okay, we'll go ahead and put that down. So this is going to be similar to the blue. You actually have to strip off quite a bit before you can actually tell a difference. So steganography is the art and science of writing hidden messages in such a way that no one even knows the message exists. This is in total contrast to cryptography, where the existence of the message is not disguised. You know it's there, but the content is obscured by encryption. So there are lots of legitimate uses for steganography. Watermarking intellectual property, that's a big one that's done fairly often. Maybe if you want to protect confidential information, you can use it. And protecting private communications. All 3 of these are totally legitimate. There are some illegitimate uses for steganography that are seen fairly often, or used fairly often. I'm not sure how often they're seen because you don't necessarily even know they're being used. But theft of data, I've had a number of cases where intellectual property from companies was sent off using steganography and nobody knew it. Hiding of contraband, and of course the contraband normally is going to be stuff like how to make a bomb or maybe child porn or something like that. And terroristic communications. So a terrorist could use steganography, hide a message in an image, post it on their website so the whole world could see it, but nobody even knew that there was a hidden message there. So there was lots of early steganography. They would sometimes take a stone and write a message and then pour wax on top of the stone tablet. And so it was really hard to tell that there was anything there. It just looked like a regular stone tablet. Sometimes they would even shave their head, tattoo a message in their head, and regrow their hair and go deliver the message. So, you know, these are two really low-tech examples of steganography, but sure enough, nobody even knows that the data or the message is there unless you would shave the head or scrape the wax off the tablet. And that's the whole idea. You gain a lot of safety if you don't even know that the message is there. So, of course, disappearing ink is one example. Literary steganography. Edgar Allan Poe was really, really famous at doing this. And I'm not going to go through this right now, but he used to go to great lengths to hide messages within his writing. So I just actually showed you the demo of stripping color bits, so I won't do that again. So now, how do you hide messages in RGB images? Well, first of all, RGB stands for red, green, and blue. And normally, when it comes right down to it, most images are composed of RGB triples, a red channel, a green channel, and a blue channel. And normally these are bytes, or values from 0 to 255. And that actually plays into the methodology for hiding the data within them, because you just have to realize they're sets of 8-bit numbers. So each pixel of the image has 3 bytes that describe it, red, green, and blue, values from 0 to 255. This is different from what we know as indexed images, such as GIF, and some PNGs actually are indexed too. You can still use steganography in GIF and the indexed PNG, but it requires a different approach, so we're not going to be going into that right now. So do you remember when we looked at the bit shaving, or the bit dropping off those least significant bits? In almost all cases, the least significant bit of all pixel data can be discarded without affecting the visual perception of the image. There's a theory known as just noticeable difference that says that small changes will not be noticed. Okay, and you saw that in real time. The least significant bit is less than 0.5% of the pixel's definition. So even in a statistical meaning, it's not statistically significant. You could consider discarding more than one bit, and as we saw in those colors that I was showing you, you can actually drop off sometimes 2 or 3 bits before it really degraded the color. For many images, discarding more than 1 bit can be done without a noticeable difference. Images that lend themselves to the loss of more than 1 bit of data tend to have busy pixels or solid shapes that are at least a mid-level brightness. So if you're looking for some sort of an image file to go ahead and use, say you're looking for the best image to hide data in using steganography, you want to try to have pictures that have at least mid-level brightness, because this will give you plenty of space to hide your data in. So with one or more bits discarded, there's room for hidden data, right? If I've stripped off all the least significant bits, or the 2 least significant bits, this gives me lots of space to hide my data. And it really doesn't matter what data I hide, whether I hide 1s or 0s. Remember, we said that these bottom least significant bits aren't really going to affect the image perceptibly. So since the least most significant bit doesn't perceptually alter the image, the bit can be set or not set without notice. The least significant bits can be used to store the hidden message, and the image into which the message is hidden is known as the carrier. So we have the carrier is one file, and the message is either a separate file, or it's just a message you might have just inserted with some sort of program. Hidden text can be hidden in the least significant bit of the carrier image 1 bit at a time. Take, for instance, the letter A, and that's decimal value 65, or as you can see in binary, 01000001. The first low bit in the carrier will be 0, the next 1, the next 0, the next 0, and so forth until the entire letter is hidden. So we can first hide a 1 in the first stripped off bit, and we can hide a 0 in the next stripped off bit, and so forth. So basically we distribute this A. Let's say we stripped off 1 bit for each RGB value. We could hide this in the first 8 bytes of RGB data that we had stripped. Now if we stripped off 2 bits from each RGB value, then we could actually store this in the first 4 RGB values. So here's an example. I've got this image of a sailboat, and I took the first 2 2/3 pixels. Okay, I've got 8 bytes here, but notice it's not a full 3 pixels. It's almost, so you have R1, G1, B1, R2, G2, B2, R3, G3, and then B3 would be for whatever the next data is that you're going to be hidden. Notice that, look at the very bottom row. What we need to do is 0 that out. Sometimes we call that bit shaving. So we go ahead and bit shave that. No perceptible difference in the image. Okay, notice everything's a 0 at the bottom now. Okay. So now what we do is we hide the A. Notice the very bottom bits, 0, 1, 0, 0, 0, 0, 0, 1. Those are actually the binary values from the letter A. So now what we've done, we stripped off the bottom bit by setting everything to 0, and we reinserted all the bits from the letter A. No perceptible change in the image at all. So remember, there are two sets of data. One is the carrier, which for our example is an image file into which the data will be hidden. The other data set is the payload, which for our example will be hidden within the carrier. The payload might be another file, a typed message, or anything else that can be represented as binary data. It's important to point out that the carrier data must be larger than the payload. My rule of thumb uses the image dimensions to help figure out how large the payload can be. First, multiply the width by the height, then that number by 3, because each RGB triple is 3 bytes. If, for instance, your image is 100 by 45, then you would multiply 100 times 45, then that number by 3 for a total of 13,500. But you're not quite done with the calculator. This number must then be divided by 8 for a final payload size of 1,687 bytes. Divided by 8 if you're only stripping one bit off or using the single least most significant bit. That means for an image with dimensions 100 by 45, you can hide a payload of size 1,687. Of course, that's my method, which I'm explaining in this presentation. I've used other techniques that can store more. But let's keep it simple and keep with the formula width times height times 3 divided by 8. We'll treat the carrier as a byte stream and the payload as a bit stream. One by one, the carrier bytes are read in. For images, these are color values. The color values will represent either red, green, or blue values, but it doesn't really matter since the steganographic technique doesn't treat them any differently. The 3 color values mixed together determine the color for each pixel or dot of the image. If you shaved off the bottom eighth of any of the color values, it will only affect the visual perception 0.4%. Nobody will notice this difference. In fact, as we've already mentioned, there's a psychological principle known as just noticeable difference. This theory says that a color change of 0.4% is imperceptible. Now we know that we can shave off the bottom of the color values and the viewer will never know the difference. Now we can illustrate the beauty of the method. For each incoming carrier byte, we start off by shaving off the insignificant bottom that we talked about. Once again, we can do this without any danger of being noticed. The next thing we do is read in a bit from the payload stream. We then replace the bottom bit in the carrier with the payload bit. If the payload bit is a 1, then we set the insignificant bottom of the color value to a 1, otherwise it is 0. We continue this process until the entire payload stream is embedded into the carrier data. Now that the entire payload has been embedded into the carrier 1 bit at a time, to extract the data, the process is simply reversed. And here is a diagram showing this process. Notice there's a carrier byte stream, and it's reading from the file 1 carrier byte at a time. Now I want to be careful. You have to skip over any kind of file header or image header information. So you would definitely notice a difference if for whatever reason you altered those the data in those sections. You got to leave the file headers and the image headers alone. But then you have your payload, and it's a bit stream. You're reading in 1 bit at a time. Okay, so the first thing that happens is the incoming byte comes in. The least most significant bit is stripped, and then the payload bit is inserted, and this goes out in the outgoing data stream. So one of the problems with the bit shaving steganography we've already talked about is a lot of people know about it, or a lot of people are familiar with it and use it. So I actually created a new method, which I call Blender, of steganography, which is a totally different and new approach. So just as a reminder, the bit shaving is a common steganography technique. It uses image files as carriers, and it replaces it. First, it strips off the least significant bit from the carriers, but then replaces that with the bit stream from the message or the payload. Various tools can be used to detect hidden messages. One example of this might be Stegadetect. It's not necessarily very effective since they need to know the exact method that was used to hide the message in order to retrieve said message. Depending on the complexity of the steganography method, this could end up being very difficult to reverse. So Stegadetect is not necessarily a great way to reverse the hiding process. There is one giveaway though that might tell you if an image has been hidden or if the message has been hidden, and that's with bit shading. So a lot of times people go through, or software goes through, and at first it strips off all the least significant bits. So the entire document, all RGB triples have the least significant bit stripped off, and then it goes through and then hides the payload bits. But with a large number of zeroed least significant bits in a row, such as would be, let's say your payload only took half of the image data, and then the rest of the image data had all of the least significant bits stripped off. This is a statistical improbability, and this is used as an indicator of the modification. So there are two ways to avoid this type of detection using bit shaving. Only shave off bits for enough bytes, since there's enough room for the message. Then, after shaving off all the least significant bits in an image and hiding the message, go back to whatever zeroed bits are left and randomly set some of them from 0 to 1. But even better than that is a new method which I am going to talk about. This will definitely avoid detection. So Blender actually alters unknown bits in a sequence of carrier bytes, not just the least significant bit or bits. And not knowing which bits have been altered makes it much more difficult to detect hidden messages. Not just least significant bits, and not always at the same bit every time. So Blender acts on a group of carrier bytes instead of just one carrier byte at a time. Number of carrier bytes in a group can change from carrier to carrier, adding variety and difficulty in detection. So by default there are 12 carrier bits, but it could be 16, 18, 20, whatever you want. So here's sort of a high-level view. The image is loaded into memory buffer. The algorithm moves a pointer from the beginning. Actually, it's the beginning of the RGB data, not really the beginning of the... But here again, we have to skip all of the file header and image header information. But it starts from the beginning and goes to the end of the buffer, or as long as it's needed for the message. The algorithm starts with one carrier byte group, and when it's finished, it will move on to the next group. So here you can see groups of 12 bytes. Here's the previous group, the current group it's acting upon, and then when it's done with the current group, it'll move on to the next group. The algorithm calculates a total for each group of carrier bytes. In other words, it just adds up the 12 bytes and gets a sum. This total is an accumulator of each of the carrier bytes values. So here's the pseudocode. It's just a loop calculating everything and returning the total. And that's the flow chart for calculating the total. The important thing about Blender is not the total for the groups, but a value calculated from that total and a modulus value. Each group thus has a hidden value calculated from these two values. The modulus value is predetermined. For example, my total might be 1234, the modulus might be 256, and the hidden value is 1232 modulus 1234 modulus 256, or 210. So from each group, from each carrier group, we have a single hidden value. And notice, since it's modulus 256, it will be a value in the byte range of 0 to 255, although it doesn't have to be. Blender depends on calculating that modulus value of the total for each carrier byte group. The modulus value equals the next message byte that is to be hidden. For instance, let us suppose that the message that must be hidden is the set of 4 characters TEST. These 4 characters have ASCII values of 84, 69, 83, and 84. Since there are 4 bytes to hide, the algorithm requires 4 carrier byte groups. Ideally, the first group will have the mod value of 84, the second 69, the third 83, and the fourth 84. So here's the pseudocode for the extract message code. It creates an output buffer, and while it's not done, you get the total for whatever group you're working with, okay? And we've already discussed that. The message value is the total modulus the predetermined mod value. And you append whatever that message value is to your out buffer. And finally, you move on to the next group. If an exit condition exists, then done is true. Okay, so that's all there is to it to extract it. It's more complicated to embed the message, and we'll talk about that actually more when we look at the source code. So here's the flow chart for how that works. So it's easier to extract than to hide a message. When extracting a message, there's no need for adjustment to the group of bytes. But for each message byte that must be hidden, the bytes in the current group must be adjusted until the modulus value of the group's total matches the message byte. So in other words, you take the 12 or 16 or whatever, you take the carrier group, and you adjust the values of each of those by either subtracting or adding one at a time until you get the exact mod value you're looking for. So let's suppose that the message byte that must be hidden in this group is 84. Now let's suppose that the modulus operation value does not match that. In order to adjust the modulus operation value, we go through the carrier bytes and either add or subtract 1 until the modulus operation value matches the message byte. As a special note, if the group total is above the halfway point, meaning that the average of the group bytes is more than half of the predetermined modulus value, then the algorithm subtracts. On the other hand, if the group total is below the halfway point, then the algorithm adds. This ensures that the carrier bytes stay within the range without an overflow. So there are variations you can apply to this, which makes it even more difficult to find and extract messages. It's easy to determine the size of the carrier data needed to hide a message. The method uses an entire group to hide a single message byte. During development of the demo program for Blender, a group size of 12 was chosen. For each message byte, 12 carrier bytes are needed. Thus, multiply the message by 12 to find the required minimum carrier size. Blender is a new approach to steganography that hides messages while making it harder to be detected. 2 important values, group size and modulus value, both of which can be changed. In addition to random bit places being altered, this makes detection of hidden messages very difficult. Future research will be steganography in JPEG images due to the wide usage of these types of images. The reason that was avoided for this preliminary presentation is because of JPEG's lossy nature. So I'm hoping actually some of you can download the Blender program, which I will make sure I have online by say Tuesday night or Wednesday morning. And I'm looking for people to start critique it and offer some help with it. Now please note that this str_str_icmp is not Linux, that's Windows. I'm looking at the Windows build, so I had to do something. I had to just make that a string compare for Linux. So let's go ahead and go down to the do embed. Okay, so here's the embed function. And first it loads the actual the message, the payload file. Then it loads the carrier data, the BMP file. Okay, now bear in mind, PNG would also be fine. I would have to link in PNG lib or something like that, but BMP and PNG should be fine for all of this data. Okay, so here we calculate the bytes that we can actually hide. The RGB size divided by the group size. We've already sort of talked about that. And we just give an error message if for whatever reason we don't have enough space. And then we call the embed message function and call save message, save BMP. So let's go ahead. Okay, so here's embed message, and this should be pretty much what the slide showed. First, for every group, we adjust the group. Okay, and after we've adjusted the group, we add the group size to the data pointer. Okay. Here's adjust group. So first, and this is for each group. First, we calculate the delta. And the reason we want to calculate the delta, it's either going to be 1 or -1. If the values are high, it will be -1, so we don't exceed the bounds of bytes. If it's low, it'll be +1, so we can go the opposite direction. Okay. So this actually just calculates the mod value. Okay, and to calculate the mod value, you just sum up the group size and the group, all the bytes in the group, and then you actually mod it with a mod number. And so here we go ahead. So we check to make sure that this particular byte is in range. Okay, if it's not in range, if we've already hit like 255 as a max or 0 as a min, we're not gonna try to adjust this, and we'll skip it. But for the entire group, what we're going to do is adjust each byte one at a time. And since we're doing it one at a time, what we do is we make sure that for every single one that we adjust, we get the mod value again. So anyway, that's sort of the summary of the method, and I'll have the source code up there sometime tonight.